Hi there. So in this video we want to talk about an important mathematical topic. It's also very important in physics and engineering and several fields dealing with what are called vectors. All right, and so vectors are very important quantities. We use them in math mostly as tools to help us solve some problems, but they are, like I say, very important in physics because they represent actual physical quantities. All right, and so one thing about vectors that I'm going to point out before I get started is that you can do everything we need to do with vectors without using coordinates at all, and you can do, or you can take advantage of using coordinates to describe vectors and work with vectors. So in this video, I'm just going to talk about the basics of vectors, what they're about, and then how to do everything without coordinates, and then in the next video, I'll do everything with coordinates. All right, so to get started, what a vector is, it is some quantity, but there's something else to it. A vector is a quantity with an associated direction, okay? And so that ends up being an important part of it. And so there's these two parts that compose a vector. There's the quantity, how big the vector is, and then in what direction it behaves. So let me illustrate why that would be important. So a very common type of vector is a force, okay? And so forces are vectors. And so why would that direction be important? Let's say you're standing right here, okay? And say there's a 50-pound force that's going to be applied to your body somewhere, all right? Well, imagine if that force just goes right here in that direction, okay? Yes, that's going to hurt your toe, but it's going to have a lot less effect and as opposed to what if that force was applied in that direction right there. Then you're going to get a big old punch in your gut and it's going to hurt even worse than that toe. All right, and so there's lots of situations in the world where we're not just interested in how big something is, but also in what direction you travel. And let me give you one other example too. Okay, another example is what's called displacement. Okay, and so let's look at another one. Okay, and what displacement is it's a directed distance. Okay, and so so think about this. If I just say a distance, if I tell you that I traveled 70 miles yesterday, that tells you something, and it tells you how far I traveled. But what if I told you that I traveled 70 miles from Roseburg, Oregon to Eugene, Oregon? You folks that aren't familiar, that's a little bit west of north, like that. So it's telling you in what direction that I also traveled. So it's not a huge amount of information, but it does give you more information. And if you think about distances, often we're not interested in just how far we went, but in what direction we traveled as well. All right, I'm not going to write out more examples here, but displacement, there's three types of vectors associated with distances and travel. There's displacement, velocity, that's a directed speed, so it's a speed with a direction, okay? And then associated with velocity is acceleration. So that's telling you in what ways the velocity is changing and in which directions it's changing. Okay, and so those will be our four basic types of vectors. There's many, many, many other types of vectors, but these four will be our basic ones that we'll use for examples and so on when we talk about the physics part of it. Okay, now you've seen in your math world so far lots of things that don't have a direction to them, so we need some way to distinguish whenever we're talking about things that have direction and whenever we don't. So we'll use this word scalars right here, okay? And scalars are just quantities, okay? And so they have no associated direction, all right? And so we'll often just use a number that will be a scalar that doesn't really have physical significance, but there are many physical quantities that are just scalars, namely temperature, okay? And so the temperature at a point in the room is just a static thing, and And so it doesn't have an associated direction. There ends up being a vector associated with temperature, often called the flux, that describes how the temperature is moving whenever it's changing in a given area or volume. And so there are vectors that get associated with it, but temperature itself is not a vector. And then also a very important set of vectors is the length of a vector, okay, like that. So that's the quantity I was referring to in the last slide, how long the vector is, or how much, how much force is there, like that 50 pounds I talked about, like that. And there's another vocabulary word for this. It's called the magnitude of the vector, okay, like that. Now with force, the magnitude of a force, you would just say the magnitude of the force. But with the motion things, the motion vectors, we get some vocabulary that you're already used to. The distance is the magnitude of the displacement, okay, and then speed is the magnitude of the velocity. Okay, with acceleration, we just say the magnitude of the acceleration, but we get these two words that you're more used to. And so try to distinguish between those. If we're just talking about how far we went, we use the word distance. If we're talking about how far we went and in what direction we traveled, we're talking about displacement. So displacement is a vector, distance is a scalar. Okay, same thing here. If we're just talking about how fast we traveled, we're talking about speed. But if we're talking about how fast we traveled in a given direction, we're talking about velocity. Okay, so these two here, like I said, these are vectors. These two here, these are scalars. All right. All right, in terms of just being able to specify vectors, just like we often give variable names to things, we'll want to do the same thing with vectors. So since we're talking about the word vector, a very common, just general letter to use is V. Okay, now the thing is, we're going to have to distinguish between scalars and vectors when in our writing, because they are very different types of quantities, especially in the physical part of things. All right, and so since we're going to have to distinguish between them, there ends up being some special notation. If you read in books, they'll usually use boldface like that. Okay, but that's easy to put in typing, but think about writing it. As you're writing and trying to do math and you're just trying to write the name of some variable, you're going to have to pause to bold that in. So that gets a little bit slow and frustrating. So what we usually do in our writing is we'll do V and we'll write an arrow over it. That's probably the most standard notation. I will warn you, there's lots of notations for vectors, and it just kind of depends on what you're reading and understand what you're reading. I personally get a little tired of drawing a little arrow all the time, so I'll usually use just a bar over the letter to denote it. But I've seen other notations. I've seen people use a little tilde either over it, over the V, or above the V to denote like that. And even in sometimes people are just doing such a high level math that they assume that the reader can distinguish between them. So sometimes they'll just use the letter V without giving special notation. I don't advise using that at all, and unless you go, later in your life, if you understand that, because then that requires a lot more understanding through the reading about which quantities are vectors and which ones are scalars. All right, so as far as my purposes go, these will be the two most standard ones right here. And like I say, I just get lazy about drawing that arrow, so I usually just draw the bar. But most books and treatments will use the arrow too. Okay, now make sure you realize you don't have to use V. Like often we'll be talking about a force, so we'll say force and we'll put a bar over it, or an arrow over it like that. And sometimes you have more than one force or more than one velocity or something, so we even can use subscripts to denote them like that. All right, and so there's lots of different notations, and you'll see different things, and it just kind of depends on the reading. Now, to denote the magnitude of a vector, okay, and so there's special notation for this, and again, there's not standard notation. It's usually one of two different notations. Okay, and so I say I have the vector v, but I want to talk about how big it is, what its magnitude is. All right, and so many books will use these double vertical bars like that. Okay, and so what that is, that's the magnitude of v, of the vector v. Okay, and just remember from the last slide, that's an actual scalar. It's the length of the vector. Okay, like that. And so then, but some books, and I've started using it more often too, is just use a single absolute value bar like that. And so that's another notation for the magnitude of vector v. And so just like, v is just a name I'm using, but if I wanted to talk about how big this force is, what its magnitude is, then I would denote that either with 1 or 2 bars as the magnitude of F1, like that. All right? And so now whenever we draw vectors, it should give us everything we need to know. So say I have this vector, I have a vector v here, and I tell you it's this vector right here. Okay, well, first of all, make sure you realize it starts at this point and travels here. That arrow is telling me something. So that arrow right there is giving me the direction. Okay, like that. And then how long I draw that vector is important. The length of that vector, that's the magnitude of v. And just remember, we have special notation for that. We use those absolute value bars, either 1 or 2 bars. Okay, like that. And so that specifies the magnitude of v. So whenever we draw vectors, ideally it gives us everything we need to know about that vector. And then two other vocabulary terms, and then we can actually start talking about doing things with vectors. But say I have this vector v here, like that. So there's these two, you can think about this vector being composed of 2 points, where the vector starts at and where it ends at. So where the vector starts at, that's called the initial point. This will be more important whenever we use coordinates, but we will use it in a minute whenever we're adding. Okay, and so this point where it ends at, that's called the terminal point. All right, and so we'll need those 2 vocabulary terms. So now let's start talking about what we can do with vectors. We want to start talking about what's called a scalar multiple, but I want to point something else about vectors too. Remember, vectors are defined by their magnitude and their direction. Okay, so their position isn't relevant, and so this vector right here that I have, I can move it around, and it's still the same vector. Okay, and so that allows us to do some manipulations mathematically in a little bit. Okay, and then the other thing I want to point out is this idea of scalar multiple. Now, don't worry about that term yet, but just think about having a vector. What are things I can do with it? I can stretch that thing out, or I could squeeze it down really small. Okay, and so that's going to be the idea of a scalar multiple. Now, what we'll also talk about is reversing the direction too. We can reverse directions with scalar multiples and still stretch it and so on like that. So yeah, let's think about having 2 things. We have a c, which will be just some positive scalar, okay, and then v is going to be a vector, okay, and what we can do is we can form a new vector, and that new vector is just going to be c times v, and that's called a scalar multiple. That's where that term comes from. So notice you're multiplying a vector by a scalar, okay, and make sure you realize what it's forming. It's forming a new vector, and that's going to be important when anytime you're dealing with vectors, is to always distinguish between whatever you're computing. Is it a scalar or is it a vector? Okay, but we'll worry about that later. Okay, so right now we're forming a new vector, c times v. Okay, now here make sure you realize c is positive. All right, and so we're not considering yet where c is negative. All right, so we have some positive number times a vector. Okay, it has the same direction as v. Okay, so the direction doesn't change, and its magnitude is c times the magnitude of v. Now that looks a little complicated, but what that means is it either stretches the length of our original vector by a factor of c, or it could dilate it if c is smaller than 1. Okay, so this is best seen with a picture here. So say here's my vector v. and to use some actual numbers. Okay, so c is just a general scalar, but let's think about what 2v would look like. Okay, so it's going to have the same, since that scalar here is positive, it's going to have the same direction as v. All right, so it's still going to point in this direction, but its magnitude is 2 times the magnitude of v. So that means it's going to double that length. I'm not going to be able to draw this perfectly, but I'm going to roughly draw a vector that's twice as long as that original vector. So I hope that makes more sense than just the notation right there. And then imagine if I had 1/3 times v. Okay, that scalar out in front is still positive, so it'll still point in the same direction. But what's that going to do? This new vector is going to have 1/3 the length of our original vector. And so again, can't draw it perfect, but that's roughly 1/3 what I started with there. Okay, and so that's the idea there. And then lastly, to say about scalar multiples, if c is negative, you can probably guess, then the direction reverses. Okay, like that. And so I'm going to do this. I was feeling bad about my pictures there a minute ago, but say I have this vector v, and I want to talk about negative 2v. And so now, since my scalar is negative, that means it's going to go in the opposite direction. So my new vector is going to point down this way. And then what's the deal? It's being multiplied by 2. And so it's going to be twice the length of v, but in the opposite direction. Okay? And I'm going to draw some better pictures on the next slide where I can take advantage of a grid. So let me show you what I'm talking about with a demonstration. Right here we're starting with a vector v right here. Okay, so it's that vector. I'm using it in the coordinate plane, although we're not using coordinates yet, just so that you can kind of see the effect of a scalar multiple. So what I'm going to do is I'm going to look at different values of our scalar multiples of this vector right here. Now you can see this note about the blue vector is 1 times v. You can't see it yet because 1 times v is the same as v, so it's overlaid. But now let's look at what happens whenever I start playing with values of c. And so the first one I'm looking at is 2. And so now we're looking at this vector right here. That's 2 times v right there. And then now I looked at 3 times v, and so I get a vector that's 3 times as long in the same direction. Here's a vector that's 1/2 v, so you can see it's half the length that we're seeing. And I typed in 1/3, although that converted it. So that vector right there is 1/3 the size. Now remember, a negative constant will change the direction. So if I type in -1, notice I get the same vector, it's just going in the opposite direction. And then there's -1/2, and so it has half the size of v, but in the opposite direction. So hopefully that makes a little bit more sense about how scalar multiples work. Okay, now we want to talk about adding vectors, but it's really important to understand why we do things the way we do whenever we're adding vectors. So we're going to have two vectors, u and v, and we're going to try to find a way to define u plus v. But the thing is, we have to define it in a way that it aligns with the physics. Remember, vectors are important physics kind of objects. Okay, now there's a kind of a catch though. There's actually two ways to look at it, okay, depending on what kind of vectors we're talking about. Okay, they end up being equivalent. Whenever we say things are equivalent, it means they do the same thing just in different ways. Okay, but there are two ways to look at it, and they're both important and worth mentioning. Okay, so let's think about the displacement. Let's think about our vectors being displacements. Okay, and so you think about u being one displacement, so you're traveling in one direction for a given number of miles or kilometers or meters or whatever. Okay, and then the displacement changes, and so then it changes to v. Okay, so that's going to be another displacement. All right, like that. And so the idea here is that we started with our vector u. So we went from, say, here to here, like that. So there's our vector u. So what that means is that we started here, we traveled in the direction kind of upright. We traveled in a east of north direction. Okay, and we ended up here, and then we turned somehow and we followed this displacement. So we're going to have this new displacement. Now let's say we turned west of south and we went a shorter distance, and so we went here, v, that's the vector v, like that. Now what we'll often wonder about is what is our net displacement, namely if we could have just gone straight to this ending point right here. So think about this. The idea is that we started here and we ended here. So if we could have possibly gone straight from our starting point to our ending point, we call that the net displacement. And it's just right there. So the blue, like I said, we call that the net displacement. Okay, like that. And that's what we consider to be u plus v. Okay. And this actually demonstrates one way to add two vectors. It's called the tip to tail rule. And I'll explain that like that, okay? And so what that tells you to do is you draw the first vector, okay? And then you draw the second vector starting at the tip of the first. All right, like that. So notice what I did. Here I drew my first displacement, and again, it aligns naturally with how we would think about displacement. So we draw our first vector, and then we draw the second vector, v, starting at the tip of the first vector. So we draw it there, and then what is the result? What is the addition? It's this vector right here that starts at the initial point of our first vector and at the terminal point of our second vector, right there. Okay, now what ends up happening, and this seems kind of confusing right now because we haven't done any actual problems. What happens mathematically, the way we often specify directions is with angles. So we might be given the angle back to the horizontal or the vertical. And so what we'll be able to do is figure out do some trigonometry to be able to describe that vector more carefully. But the way you get to doing that is you draw the vectors out like this, and then realize that their sum is the vector that starts at the initial point of the first and goes to the terminal point of the second. And so you draw that as a diagram, fill in all the information you have, and then that's when you start using the trig. Okay, and the other way to think about adding vectors deals with thinking about those vectors as being forces. So with forces, we usually think about two or more forces acting on a point, and it leads to what's called a net force. Okay, so think about this for there being a point right here. All right, and you have one force that's acting on it this direction right here, like that. Okay, like that. So there's going to be your F1, or you could use U and V too. Don't feel like you have to use F1 and F2. All right, and then, but think about there might be a smaller force acting back this way on that point that we'll denote by F2. Okay, like that. So in a way, this force is bigger, but this force is going to counteract it a little bit because it's going to act in this direction to push back on it some. And conversely too, this force is acting that way in a pretty strong fashion, but it's going to abate that force. So the combined effect of these two forces right here on that point is called the net force. And the net force would be the sum of those two vectors right there. Okay? And so whenever we talk about net force, we're talking about the sum of two forces. Or more. We could have more than two forces. Okay, now remember what I said earlier. The position of a vector isn't a defining factor, so I can think about redrawing this picture. Sorry, I thought I could move that, but I can't. So I could think about redrawing this picture. Here's my point right here, and I could draw it where both of their initial points are on that point. So here's my F2, and then here's my F1. Okay, I'm sorry if I didn't draw that perfectly. Okay, but that's the idea there, is that I can draw them where their initial points are both on that point. So then you can kind of get an idea about what's going on here. Because the way those two forces are going to interact with each other, the resultant force, or the net force, is going to come out somewhere in here, right? Acting somewhere like that. Okay, so you can actually quantify this though by drawing a picture. What you can do is you can draw a parallelogram. So you can redraw F1 over here on this side. And again, sorry if I'm not drawing things perfectly. And then you can draw F2 over on this side, and you see you get a parallelogram. And then what the resultant for what the net force is it's the vector that stretches to the other diagonal. Okay, notice that all three of these have the same initial point. That helps you get the direction of the net force. And so there's our net force right there. And so that vector right here, that's going to be F1 plus F2. And again, in actual problems, you'll have information where you can take advantage of some trigonometry and geometry to figure out actual quantities and so on like that. Then I'm going to do some examples right after that. Okay, and so this adding vectors this way, we call this the parallelogram law. Okay, like that. Now, one important thing about either one of these are two equivalent ways to think about how to add vectors without coordinates. All right, and the important things about this, they're equivalent. So if one of these makes more sense to you than the others, feel free to use that. So I could use the parallelogram law to add two displacements. And so a minute ago I had this displacement here, and then I had this displacement here, right? Like that. Well, make sure you realize I could draw in my parallelogram right there, and the diagonal of that parallelogram is going to give me the exact same thing. All right, and so that's the reason they're called equivalent. So, like I say, if one makes more sense to you than the other, feel free to use it. I always like to have as many tools available to myself as possible, so I like to know them all. So I want to show you how this works with a little demonstration. What I'm going to do in this demonstration, I'm going to show you the parallelogram law first for adding two vectors, and then I'll show you the tie-in to the tip-to-tail rule that it gives you the same answer. So anyway, here I have a vector u here and a vector v here, and I want to add them together. So if you're using the parallelogram law, you draw them so that they have the same tail. All right, and then remember you form the parallelogram, basically just redrawing these two vectors on the other sides over here. And so I subscripted their names with a D to mean duplicate. Okay, so I get that. And then to see what the sum of those two vectors are, you start at the common tail and you go over and draw the other diagonal to the common tip over there. So there's your vector u plus v. And then notice if I move my vectors around, then of course that's going to change the result of the sum too. Like that, and so it could be, you know, over in any position around in here. And same thing, I could move this vector around as well, and then that will affect what's going on. All right, now to see the connection to the tip-to-tail rule, notice that we're getting this vector that's on this diagonal. Okay, if you're doing tip-to-tail, you don't draw the vectors with the same tip. Okay, and so let me get rid of some of my stuff here for a second. But let's go ahead and keep that sum on there. What we do is we draw V starting at the tip of U and going and drawing it in there. All right, and so there's V drawn starting from the tip of U. So notice that they do look the same if I put the original V back in there. So those are the same vectors, and so notice if I start at the tail of the first vector and go to the tip of the second vector, it gives me that same vector that I got whenever I did this with the parallelogram law. So they give you the same result either way you do it. Now, before getting into some examples, we want to talk about subtracting vectors as well. And subtracting vectors combines the two ideas of adding and a scalar multiple, because remember, just like with numbers, we can always rewrite a difference as plus the opposite. And so we could rewrite this as u plus negative v. Okay, and so remember, all this vector does is this just reverses the direction. Okay, and so whenever we do that, let's say here, I'll have a better demonstration in a minute, but let's say here I have vector u, and then here I have vector v. Okay, and I want to subtract those two vectors. All right, and so since here is my vector v right here, then to do u minus v, I want to do I want to find what negative v is. So let me do that in a different color. So negative v would be right here, basically the same vector, just in the opposite direction. Okay, and so again, right here, I'm trying to find u minus v, right? But that's equal to u plus negative v. So why is that important to point out? What I'm doing now is I'm adding these two vectors, okay, like that. And so I'm going to redraw over here. So we're adding those two vectors, and so here I have my negative v, and here I have my u, like that. And so since I'm adding them now, I would use the parallelogram law. And so, or the tip to tail rule if you like that better. Okay, and so now where is u minus v? It's right here. Sorry I didn't draw that very well, but it's right there, and so that vector right there is u minus v. Now there's a nice connection between the sum and the difference, and basically what we can do is we can use one parallelogram, the parallelogram that we use for adding, to end up doing subtraction, but I want to point that out on the next slide. So yeah, if I have these two vectors, u and v, so remember to form their sum, I draw the parallelogram determined by them, and then the diagonal of that parallelogram that has the common tail of u and v is their sum. Okay, but remember what we did whenever we subtracted. We went and we got negative v, and then we added those two together, so we formed the parallelogram down here, right? And then u minus v is u plus negative v, so it's this vector right here, right? But one thing about vectors that's nice to be aware of is you can move them around in space and have the same vector. Vectors are only determined by direction and magnitude, not location. So what we can essentially do is take this vector right here and move it up. Okay, now if you think about it, I'm going to summarize this in a minute. If I move this vector up into the parallelogram, it's going to form the other diagonal, and that's what's nice about this. Okay, so let me summarize that, because I know a lot of those diagrams look pretty confusing by this point. Okay, but the nice thing is whenever you're talking about two vectors, u and v, you can actually picture their sum and their difference in one picture, in one parallelogram. So as always, you can form the parallelogram from the two vectors. Okay, the sum will be the diagonal that goes from their common tail to the other corner or the other vertex. Okay, so that will be u plus v. Now, the difference, you got to be a little bit careful, but it does go along the other diagonal. All right, and so u minus v is on the other diagonal. You just got to keep up with its direction. So it always goes to the first vector, the vector that you're subtracting from. So it goes here. So it'll always start at the second vector and go to the first vector. And so that's u minus v. If that wasn't clear what I was talking about a minute ago, here's what I'm calling the first vector and the second vector. So the difference goes from the second vector to the first vector. And again, if you're confused by that, it's because of going through this process, so it goes in that direction. All right, now we can look at an example. Now I'm just going to do a math example right now. We use vectors to solve all kinds of practical problems. After I show you how to do things with coordinates, I'm going to do a separate video with more word type problems, because it's kind of up to you how you want to approach them. Be aware though, no matter what, there's quite a bit of trig, because of the way we specify direction with vectors is often with angles. Okay, so anyway, in this problem we have u and v pictured like this, and then we want to find u plus v and u minus v, and then think about what this is saying. Remember, this means magnitude, so basically this is saying that the length of u is 10, whatever units we're in, and the length of v is 7, again, whatever units we're in. Okay, so what this statement right here is saying is that the length of u is 10, like that, and the length of v is 7. Okay, now in order to give direction, like I said, we usually specify angles, and the way this problem is specifying direction is we think about, we have some kind of horizontal line, and the direction's being specified in terms of some kind of angle from that horizontal. And make sure you realize these are coming, from two different directions. And so U is going to the right, V is going to the left is what I'm trying to get at there. Okay, that's going to affect how we answer the problem, but we'll worry about that when we get there. Now, the way we solve this problem is going to look pretty complicated at first, but I will point out they basically always follow the same format. So be aware of that at first, but whenever you first see this about how to solve this, it is going to look a little bit complicated. Okay, so the idea here is right now the first thing we'll do is we'll try to find U plus V. Okay, and so the idea here is, again, we have this horizontal here, all right, and then I'm going to exaggerate things a little bit just because I'm going to need some more space. So here's U at 32 degrees, okay, and then here's V at 44 degrees, like that, and I want to add these two vectors together. Well, how do I add? I can form the parallelogram, like that, and then I'm trying to find the vector that goes along this diagonal right here. Okay, now the key thing is whenever you have a problem in a certain kind of format, you want to answer in that format. So notice how information's given to us. We're given the length of each vector and we're given the angle from the horizontal. So we want to answer in that same format. So the two things that we're looking for right now is we want to say how long this vector is, and then what its angle is from the horizontal. And notice that vector is probably tilted to the right, so we're going to want to find that angle right there. So those are the two things that we're looking for. Keep that in mind as we go through this process, because like I say, it looks pretty complicated whenever you first see this. All right, but I promise all the steps are always the same whenever you do this. Okay, so the first thing we're going to do, our first objective is going to be to find the length of this vector right here. All right, but there's some basic stuff that we can get based on parallelograms. I'm going to try to get that vector out of there too. There it goes. Okay, so the first thing to notice is here I have this 44 degrees from the horizontal. Here I have this 32 degrees from the horizontal. And an entire line makes 180 degrees, so we can figure out what this angle is right here. All right, so to get that angle there, what do? We just do 180 minus 44 minus 32. If you can calculate that, that's going to give you 104 degrees. So that's telling me that this angle right here is 104 degrees. Okay, now you got to be really careful. We're talking about a parallelogram, and be careful about your pictures. This diagonal that we're looking for right here, it will only that line will only split that angle in half if this is a right angle right here. Okay, but notice it's 104 degrees. It's not 90 degrees, so it doesn't split that angle in half. And so be careful about that. All right, but there is a property of parallelogram. There are some properties of parallelograms you can take advantage of. Is their opposite angles are equal. So this angle right here is also 104 degrees. Okay, and a very nice property to keep in mind is that the angles in any quadrilateral, any four-sided figure, add up to 360 degrees. Okay, and so these two angles right here comprise 208 degrees. Okay, so we have this 208 degrees, all right, but all the angles in that quadrilateral have to add up to 360 degrees, so we can subtract those two angles from 360, all right, and so we get 152, okay, but since opposite angles have to be equal, that means that these two angles right here have to combine to 152 degrees equally. So what can we do? We can divide that by 2, like that, and to get 76 degrees. So in terms of our purposes, this is the key angle, but in general, we know both of these are 76 degrees. Okay, like that. So that's all the angles in that quadrilateral. Now I will tell you, these 104s actually won't be that important until we get to the answer part. We might have to use them. Okay, so anyway, the key angle right here is this 76 degrees. All right, because now we got to remember what we're looking for. The first thing we're looking for is the length of this diagonal right here. Okay, and so the key thing to notice right now is that we have a triangle right there We know its angles. We know one of its angles, and we also know these two sides right here. Okay, you might not realize it right now. I'm about to redraw everything because everything's so cluttered. Okay, so all I'm going to do right now is just draw that triangle, and I'm going to forget about the whole quadrilateral for a second, the whole parallelogram. Okay, so we have this situation right here. Here's U. Remember, this is actually V over here, like that. Okay, and we know this angle 76 degrees. I kind of like using that white right there. So we got that 76 degrees right there. And what we're trying to find is the length of this diagonal line right here. Okay, now a minute ago, why did I claim that we know the sides? Well, again, right here is vector u. Okay, and what do we know about u? Its length is 10. And so right now we have a length of 10 on that one side of the triangle. Okay, and then remember over here on this side, this is really the vector v. What's its length? Its length is equal to 7. So we have this length right here equal to 7. So what I'm trying to get at here is that we have a triangle. We're trying to find this side. Sorry, that's 76 degrees. I drew it obtuse. Okay, and so we have a triangle with an included angle of 76 and its two sides that are including it are 7 and 10. This is a side angle side triangle. All right, and if we're trying to find this opposite side right here, the length that we're trying to find that length, so we'll call that x. That's a law of cosine situation. Anytime you have side angle side, you can always find the side opposite of the given angle with the law of cosines. And so you might have to look up the law of cosines to remember, but the idea here is that the opposite side squared is equal to the sum of the squares of the sides minus twice the product of the sides times the cosine of the included angle, like that. All right, now it's just going to depend on, if you're given this as a problem in class, it's going to depend on how accurate the problem wants you to be. But what you can do is you can compute this single number all at once. And so we have 10 squared, which is 100, plus 49, and then minus, well, here, let's give that exact. So that's going to be 149, and then minus 140 cosine of 76. Okay, like that. And now, since we're trying to find x, we would take the square root of that. And so, oops, x isn't a vector. Remember, x is the length of the vector. Some people might, instead of using x for this, they might say the length of v, the length of u plus v. I misspoke right there. Okay, but then that becomes a longer thing to write. Okay, but anyway, so we'll get x is equal to the square root of 149 minus 140 cosine 76 degrees. So that's exact if you want to keep it that way. Now here's what I do, especially if you're allowed to keep things, if you're going to be answering to a certain accuracy in decimal form. Okay, so the only calculator I could find available was my TI-83, but here's me computing the answer, all right? So that's not the crux of the matter, however you get the answer. The key thing is you don't want to round this number. You could write it down, round it. I usually round it 2 places, all right? So that's about 10.73. But the key thing is we're going to have to use this number in a minute. You'll see. We don't want to use this 10.73 or 10.7, or even if you wrote out all of those decimal places. Okay, we want to save as much accuracy as we can, and at least on the TI calculators, they actually store more digits than they display even. So we want to save as much as we can. So what I do in these cases, I use what's called the store key. So I hit store like that, and then what you can do is you can give that a letter name. Okay, don't use X on your calculator, though it can mess up the graphing calculators. So I'm just going to call it A. So you hit the alpha key, and then notice, here's the letters for the alpha functions. You can give it any name you want. I strongly advise not using X, Y, or T, though, because those are used in the graphing features, and I've seen people have trouble with that. So anyway, I store it in A, like that. Okay, and now what that allows me to do is anytime I want to compute with that number, anytime I want to compute with this number, then, just say I need to multiply it times 5 we won't need just to do that. We'll have to do some trig with it. But if I wanted to do that, I can just type in 5 times a. And the advantage to this is it's going to use not only all of those decimal places, but even more that it stores numbers to. And so the key thing is here is if you use some rounded version and start calculating it, since this number has some inaccuracy in it, then any calculation you do with it is probably going to have even more error in it. So you want to avoid using rounded numbers. When you want to round numbers is at the end. If a problem tells you to round a certain number of digits, then yes, you do round, but wait until you get to the answer to do that rounding. Okay, so this is about 10.73, but remember we have this stored in the letter A that we can use it to get more accuracy. So what this is right now, that's the length of U plus V. So we know how long the sum is. It's about 10.73 units, whatever units we're in. Okay, so what do we need now? What we need is we need to know this angle of tilt down to the horizontal that it's at. Okay, and what we can do is we can still keep using this triangle. Notice that we already know that the angle right here is 32 degrees from U. Okay, if you're having trouble seeing it right here, we know that this angle is 32 degrees. All right, so if I can get just this little angle right here, okay, and so if I can just get this little angle right here, then I could add 32 degrees to it to get the angle that I'm looking for. Okay, and so notice that little red angle right here, it's embedded in the triangle we were working with. So we can keep taking advantage of trigonometry laws to find that. Okay, so let me just redraw here with more information in it. It's not going to look like more information, but we have this triangle here. So we know this angle right here is 76 degrees. We know that this is 7. This is the length here is 10. And now I'm not going to write, this is about 10.73, but I'm just going to write x, okay? And since I stored it in the letter A, you might want to use the letter A. That's up to you. I'm saying that could be a little bit confusion. All right, so, and the key thing we're looking for right now is we're looking for this angle. All right, so remember that this side right here is known. It's that approximately 10.73. So now we use law of cosines to find the opposite side, but now we know an angle and its opposite side. Anytime you know an angle and its opposite side, and you're looking for trigonometric quantities, you would use the law of sines to find what you're trying to find. So we're trying to find this acute angle right here. So remember how this law of sines works. You write the sine of an angle over its opposite side. Okay, like that. So the law of sines here would say that, let's give this a name. Let's call this theta. Okay, and so it would say that the sine of theta over 7 is equal to the sine of 76 degrees over x. And just remember, we know what x is. We have it stored on our calculator, at least I do. Okay, and we're trying to find theta here. So we would need to isolate that sine of theta. And we would multiply both sides by 7. So we have 7 sine 76 degrees over x. And then to get theta, we would invert the sign. And so theta, its exact value is the inverse sine of 7 sine 76 degrees over x. If you really wanted to be super exact, for x, you would write this expression right here, and that would give you a completely exact formula. And so now this angle from the horizontal is this angle plus 32 degrees. So I'm going to go to the next slide to answer the sum part of this. But one key thing to realize is how do we answer this problem? Okay, and I mentioned this before. The way we need to answer this is we need to give the length of whatever our vector is, and then we need to give an angle from the horizontal. And all it is it's this angle plus that 32 degrees. Okay. All right, I just decided to erase all that and go from here, but I wrote down what my numbers are, okay? So what I'm going to do in this problem is I'm just going to, in terms of the answer here, I'm going to go, I'm going to draw the result, okay? And so the point is that here I have u plus v, okay? like that. Its length, it just depends on where you see the problem and how it's specific they want you to answer. So if it's left open, I usually answer to 2. So we could say approximately 10.73. But if you really wanted to cover your bases, then you could say the exact answer is the square root of 149 minus 140 times the cosine of 76 degrees. Okay, now we want to give this angle, and just remember what we said, it had to do with that inverse sine, but we needed to add that 32 degrees on it. So it's 32 degrees plus the inverse sine of 7 sine 76 degrees over, you could use x or a since I stored it as a in my calculator like that. Now the person reading your answer is not going to know what you mean by this. Now you could say a equals this, and then that would help them like that. Now I want to show you about how to use that alpha key to get your approximation here. So the key things we want to know approximately what that angle is. Okay, so here we are, and so we need to do 32 times plus that inverse sine to get our angle. So we have 32 plus the inverse sine, again make sure you're in degree mode, and then we have 7 sine of 76. Make sure to close that angle there. If you type divided by a right now, you'd get a different answer. So make sure to close your angle, and then divided by, and see, instead of typing in 10.73 or even that long decimal, I can say just a divided by a like that, and then that'll give me my angle. Okay, now again, you're just going to have to look at whatever problem and how they want you to answer. Your instructor might have an answer format like that. So you could answer it as 10 points, if you wanted to say to 2 decimal places, you might say that that's 71.27 degrees, okay, like that, or another number of places. That's called decimal degrees. Remember, some people like for you to use minutes and seconds, and so on the TI calculators, the way you get minutes and seconds is you go to the angle menu right there, and then notice there's this key right here that says 2DMS, and so in that case, you would answer the problem as 71 degrees, 16 minutes. If I usually have students round to the whole number of seconds. Sorry, my video holder is not that great. But 71 degrees, 16 seconds, 16 minutes, sorry, and then you would round that to 19 seconds. Okay, so again, it just depends on the format that whoever's asking you to do the problem wants the answer in. All right, so I'll just give it in decimal degrees here, and so I would say that that is about 71.27 degrees, like that. And so there's our answer. There's other formats, it's just going to depend. And so, but there's a description of that vector. Notice what I'm giving. I'm giving its length and its direction through an angle. And so that's what specifies a vector, and so that's how we could do that. Okay, now we're not even done. Now one thing here, this seems complicated, but let me outline the process because it's always the same. These steps will always be the same, is that if you're trying to add 2 vectors, now you could have different formats for the given information, but if you're trying to add them, you can use the parallelogram law right there. So you can form that parallelogram. I'm going to come up here to this top one, and so here's the basic steps. You're going to form the parallelogram, okay, and then you'll always be able to, from given information, you should be able to find this angle right here, okay, and then just remember that angle is the same as that angle, all right, and then the angles in a parallelogram add to 360, so you subtract basically twice this angle right here from 360, all right, and then divide that by 2 to get each one of these angles. Okay, once you have this angle here, then you'll have a triangle right there. You'll know the 2 sides, the lengths of the 2 sides, and the included angle, so you'll be able to use the law of cosines to find the length of the vector. Okay, and then once you have the length of that vector, you'll have, you stay with the same triangle, and you'll have this side and its opposite angle. So then you can use the law of sines to find either one of these angles, depending on what format you're needed to answer in the angle. So once you have these angles, then you'll be able to specify the direction of the sum using those angles. It just depends on what format you need the answer. Okay, so now let's look at how we do the difference. All right, now what we're going to see is the difference will follow pretty much the same pattern. So you got to remember how we do difference. You can use the same parallelogram. That's the key thing here. The direction on this one's going to be a little bit strange, okay? So to do the difference, just try to remember it's the other diagonal, okay? But we got to get its direction correct. So it starts at the second vector. So again, I forgot to label what I'm doing here. So here I'm doing u minus v, okay? And so as far as the difference go, it starts at the second vector and goes to the first vector. So in terms of the direction of this vector, u minus v is going to go that direction. Okay, now this, as I was doing this one actually go a little bit shorter in this case, because remember, we know this angle is 104 degrees right here. Okay, so we don't even have to do any work to figure out the length. We have to do some law of cosines work, but remember, in the last problem, we had to figure out a bunch of angles first, is what I'm getting at. So to get the length of this vector, remember, we know the length of this side, it's 10, this side is 7, and we have the included angle, so we'll be able to get this length right here in one step. Okay, so let's just go over and draw our triangle now. All right, and so like that, and so we have here's our triangle, and so we know that this is 104 degrees, and then the length here is 10, the length here is 7. Anticipating my problems from last time, I'm just going to call this capital A. Okay, like that. And so what does the law of cosine say? It says that a squared is equal to 7 squared plus 10 squared plus, not plus though, sorry, I was thinking of something, and then minus 2 times 7 times 10 times the cosine of the included angle. So cosine of 104 degrees. Okay, and so we see that 149 again, and then we see the 140 cosine 104 degrees, like that. And so then to get the length of A, we take the square root. So there's the exact answer right there, and hopefully you understood how I did the storing, so I'm going to go ahead and do that without posting it in the video. But so to get the length of A, we have the square root of 149 minus 140 cosine 104, okay? And we can get that approximation, but I would highly advise storing it into some letter. You don't have to use A, okay? But I always usually do just give myself some reference point to help me make sure things seem reasonable too. Okay, now for the direction of u plus v, this one's a little bit tricky because we got to figure out if that thing's tilting down or tilting up. Okay, I just drew a rough picture there. So this one's going to be a little bit tricky. We might have to figure out some more angles to see this. All right, so by the way, too, I'm just kind of winging it. I haven't pre-worked out this problem, so we will have to try to figure out the way that thing's tilted. Now, one thing is, and see what's a little bit tricky here is that this side is longer, like that, but it's tilted at a smaller angle, okay? And then this one's at a bigger angle, except we also have that 104 degrees right there. And so, it's still not the best angle picture right there, but it's a shorter vector, okay? Like that. And so we have I'm sorry, not 104 degrees, 44 degrees. I don't know why I'm putting all that detail in there, but I think it might help. Okay, and so the key thing is this angle right here is 104 degrees, okay? And then we know the length of this, it's about 13.52, and we just called that A, all right? And so what we're going to do here is we're going to find these angles right here and see if we can help use those to figure out the way that thing is tilted. Is it tilted up or is it tilted down? Okay, so the key thing here is that we know this angle and its opposite side, okay? And what that'll allow us to do is to find these two angles. So let's give them two names right here. So we'll call this one theta, or why don't we, or yeah, we'll call that one theta, and let's call this one gamma. Okay, like that. So let's see, for theta, we could use the law of sines. We have the sine of theta over its opposite side, uh, which would be 10. Remember, this length is 10 and this length is 7. And then that's equal to, remember with the law of sines, you always, for one of your ratios, you use the two known things. Okay, and so we're going to get the sine of 1 over 104 over a, like that. So in this case here, you can go through those same steps as last time, but we have theta is equal to the inverse sine of 10 sine 104 degrees over a, like that. And so in terms of approximating here, I would type that in. So we have inverse sine of 10 sine 104 divided by a, so I would use that alpha key to get that. And then whenever you do that, you get about 45.85 degrees. Okay, like that. Now again, I'm going to store that. I don't want to use the same letter because a is something else in the problem. So I'm going to store that. Let's see, we used theta, so why don't I use t? T's not always the best letter to use though. I'm just going to use b and c for these next two angles. Okay, so what I'm going to do, well, okay, so I'm going to use b for that. And so what I'll often do is just remind myself what I stored it into. Okay, and then for gamma, we have that the sine of gamma over 7 is equal to the sine of 104 divided by a. So if you think about going through those steps, you would get that gamma is equal to the inverse sine of 7 sine 104, 104 degrees, divided by a, like that. Okay, so all you got to do is change that 10 to a 7. Like that. If you know how to bring up previous lines, you could just do that or just retype the whole thing. Okay, like that. And that's about 30.15 degrees. Okay, like that. And so I'm going to store that into the letter C. And so we do that. Now we got to figure out the angle of tilt of this. And the key thing is, if you're wondering, we're trying to figure out if this thing is tilting down. Because see, whenever we answer the problem, angles are given from the horizontal. So we need to figure out if this thing is tilted down, where we need to draw it that way, or is it tilted up, and that's what we got to do right now. Now, the one thing you don't want to do is just say it's obvious. It does seem pretty obvious this thing is tilted upward, okay? But you could have a drawing error, especially if you're just drawing roughly. So now, one thing you can do, it just requires knowing some stuff. But one thing you could do is get a scale drawing of what's going on. Okay, and so here I used a computer program to tell me what was going on. And so here's my vector u, here's my vector v. Now this program doesn't draw the difference using the parallelogram law, where it would draw from that tip to there like that. Okay, it draws it starting at the origin here, but you can see that angle's tilted. That's this vector right here is the difference, and it is tilted above the horizontal. So if you have a reliable drawing, that is one way to do it. Okay, but let me show you a way you can actually reason out how you do this. Okay, and so let me get rid of this picture here. All right. The answer is actually pretty basic once you see it, but just remember that this angle right here is about over 45 degrees, okay? And so if we go back to our original picture, remember here's that horizontal line, okay? And then here's the vector v, okay? And it's making that 44-degree angle, okay? Now I say the answer is pretty obvious, but we got to remember some basic geometry here. Say I redrew the horizontal right at the tip of V now. Okay, like that. So there's the horizontal just written up higher. Okay, and there's a geometric property. These two lines right here are parallel. Those are two horizontal lines, so those are parallel. And so this line right here forms what's called a transversal of two parallel lines. And so what that means, it's called the property of alternate interior angles, that here we have a 44-degree angle. And so this angle right here also has to be 44 degrees, okay? But u minus v is going this way, and it's over 45 degrees, so it's bigger than that 44 degrees. And so that's telling you that this angle has to extend up above that horizontal. So if you're having trouble following me there, remember that angle right there is about 45.85 degrees, like that. And so that's how you can justify that u minus v actually goes above the horizontal and not below the horizontal. And then also just preparing for the answer too. So remember, we want to give the length of the vector, which is right here, okay, that letter A, all right. And then for the angle, since the vector, the u minus v extends above the horizontal, in terms of the answer, we're going to want to give this angle right here, okay. And so notice that we have this 45.85 approximately. If we want to give that angle exact, we would write it this way. Okay, and so that's that. But to the horizontal, we use up 44 degrees. So in terms of the angle above the horizontal, it's going to be that inverse sine of 10 sine 104 degrees over A. But then we want to subtract that 44 degrees. Okay, and so in approximate form, that's going to be approximately 1.85 degrees. So now we're ready to answer the problem. So if we wanted to answer this problem with the question, we want to say what u minus v is. So remember that its length is the square root of 149 minus 140, the cosine of 104 degrees. And then depending on how many places you're asked to approximate it to, I'll give it to 2 decimal places. But if you remember, that was about 13.52, right? Like that. Okay, and again, now one thing too that's going to be important in applications is if we have units, like if things are in feet or pounds or something, then we would include the units right here. Okay, and then if you remember this angle right here, we said on the last slide, that's about equal to, or it's exactly equal to inverse sine of 10 sine 104 degrees over A. Now, if you're going to write that, make sure to say what A is. Okay, but then we need to subtract off 44 degrees, and then that is approximately equal to 1.85 degrees. And there's our length and our angle for our vector. Okay, so that pretty much does it. Now, one thing to keep in mind, this is the way to do things without coordinates. In the next video, I'm going to show you how we can use coordinates to add and subtract. The actual adding and subtracting step is really easy once you have coordinates. But always remember that you want to answer a problem in the form that it comes. And most practical problems with vectors come in these kind of formats where you're given lengths and angles. And so where the trigonometry will come into play is getting the answer in the format that the problem came. And so we'll have to use our trigonometry to get back to that form. And so we want to always keep our trigonometry skills sharp, especially whenever we're dealing with vectors. All right, so I hope that makes sense. And it is really just that pattern of working with the parallelogram and going through those steps that I outlined. All right, so I wish you the best.